For the people who had technical errors with the part 2 of exam 1, when are we supposed to get our grades for that part 2?
I didn't realize that you didn't have them already. So if you will send me an email, I will make sure that those are showing for you. So yeah, just send me an email and make sure you say specifically that it's for folks with technical difficulties, because then I'll check not just you, but everybody who had technical difficulties.
Okay, thank you.
Designate you to send me that email. That would be awesome. Okay. This last bullet here for exam 2 is just a reminder that you guys have a lot of resources available to you, not just me. So I do have office hours Wednesday this week. I will also be adding some more office hours, so stay tuned for those announcements. But in addition to me, Honor is giving SI sessions as usual 3 times a week. And he has sessions on Monday evening, which is this evening, on Wednesday evening, and on Thursdays at 12:30. And then also just a reminder that the Campus Learning Center has drop-in hours for tutoring every single weekday, Monday through Friday, and also on Sundays. And you can find their schedule and the hours that they're open here. And there are tutors who are available specifically for this class who are there during all of the drop-in hours. So you can get personalized one-on-one help by just dropping by the Campus Learning Center pretty much anytime business hours are open, and then also sometimes on Sundays. The last announcement that I have for you guys is just to let you know that I did calculate midterm grades on Friday, and I entered them into Banner on Friday, so you all may have seen those already. They did include quiz 4, and they did include your Achieve assignments up through the end of chapter 5. But I wanted to be clear about this, that your Canvas gradebook has not been updated. It is actually not trivial and not straightforward to match up Canvas with other things. And in general, you should always be suspicious of the grade that is shown in Canvas, because Canvas, especially not the grades for individual assignments. Those grades for individual assignments you can feel confident in, and if you have a question about, you should ask about. But anytime there's like a category in Canvas, a category grade or a total grade in Canvas, you should be suspicious of that category grade or total grade, because Canvas sometimes does not pull the right collection of material to do those calculations, whereas I always pull the right material to do those calculations. Once I get Canvas updated, like for right now, for example, your quiz 4 scores have not been released yet. So once I get Canvas updated, I will post an announcement, and I hope/expect to be able to get to work more on that later today, but it might not be until tomorrow or Wednesday when I get it done. And I'll talk more about both of these topics on Wednesday. Does somebody have a question, or is it just somebody's mic accidentally on? Okay, I think that's a mic accidentally on. Okay. And regarding grading and Canvas, I will be releasing grades for all sorts of different things that haven't been released yet. For example, the Quiz 3 booster. And I'll talk more about both of these things on Wednesday. Okay, so I want to kind of make everyone have a moment of reflection, because we are halfway through the semester. So just a moment to pause and reflect on where we've been and where we're going. And not only because we're halfway through the semester, but we're halfway through course material. And we're at a moment in time in this course where we're really going to be able to shift focus and shift gears a little bit. So I'm going to try to put this into some perspective for you guys. I'm not going to take very long to do this, because I want to spend most of my time today looking at new material for chapter 6. But here I've put up this, the first 5 chapters in your textbook. These are the chapters that we have already completed and should feel familiar to you. Looking ahead, as I need to get through chapters 1 through 10 this semester so that you guys can be prepared. Hey guys, somebody has their mic on and I can't see who it is from my end. So can everybody please check their mics and make sure that you're muted? Holly, if you could make sure you're muted, that would be great. Let me see if I can get to this a different way. Okay, thanks, Holly. All right. Oh my gosh. All right, back to the slides. All right, so where we've been is these first 5 chapters. And as I've mentioned, we need to get through 10 chapters to make sure that you guys are well prepared for next semester. So these 6 through 10, I'm also showing you here to show you where we're headed. We are exactly at the halfway point, both with the semester timing and with our content timing. So we're doing great in terms of timing. But I want to take this pause point and show you guys a couple of different things that we can tell, even just from the names of these chapters, about where we've been and where we're going and why it's kind of a perfect moment to stop and reflect a little bit. So I took our same chapter titles, and now what I've done is highlighted all of the functional group names in green. And you can see that where we've been has been much more generalized. We've been talking in very general terms about the structure of different compounds, about fundamental concepts within organic chemistry that we can apply to lots of different functional groups. And we did spend a little bit of time in chapter 3 talking specifically about alkanes. But now, as we shift into chapter 6 through 10 and beyond, we're really going to be more focused on specific types of compounds or types of features within compounds. The other thing that means is that we have really been in a place where we've been focused on structure. We've been focused on generic things, either generic properties of molecules or on generic concepts that we can use as a foundation for the rest of the course. But from here on out, our focus is really going to be shifting, and it's going to be about reactions. So a lot of folks think that this is the more exciting, more interesting portions of the course, and it is going to be kind of how we move forward for the rest of this semester. And also next semester, we'll be heavily focused on reactions. And by reactions, we can think about these from kind of 2 different perspectives, all kind of framed around functional groups or types of molecules that we're going to encounter. And we can ask, so how can we make a reaction? Sorry, not a reaction, a particular type of compound. How can we create or synthesize a particular class of compounds or a type of functional group? What reactions can we use to be able to build a particular feature into a molecule? That's one type of reaction set that we're going to learn. And that's really going to be about how to synthesize things. The other type of reaction is, say we have a functional group or a type of feature in a molecule that we know about already. What are the different types of things we could do with that, right? So what reactions can a particular functional group do? And these are really related to each other, obviously, because they're all about reactions and converting one type of a feature into another type of a feature. But we'll really break these down into how to synthesize a functional group and then what reactions can that functional group do. The other thing I want to point out is that so far, we really have only discussed one reaction, and that's the free radical halogenation of alkanes, a way to introduce a halogen group into hydrocarbon molecules. From here on out, we are going to kind of learn a few more reactions in chapter 6 and 7. And then starting in chapter 8, it's going to go up exponentially, where we're going to learn lots and lots of reactions beginning in chapter 8. So with that in mind, I want to be really cognizant of a different shift in how we can think about these things. So these are kind of the 2 blocks that I had up on the last page, where we've been about fundamental concepts and generic features, and where we're going about reactions that are either making a type of compound or using a type of compound. And recognize that with these new types of a focus, this new focus on reaction, we're going to be able to ask new types of questions, and you guys are going to need to develop new types of skills. So I put up here just a couple of different types of questions that you guys can expect coming up in the future chapters, which are things like, if I give you a substrate and a product, can you tell me the reagents that I would need to do that conversion? Or kind of the opposite of that, if I give you the substrate and the reagents, can you predict the product? And are there any stereochemical consequences that you should be able to predict with that product? We've seen questions already, like draw the mechanism for a particular reaction. And this question is going to become all the more important moving forward for the new kind of shift in focus to reactions. The other type of new question that I could ask you guys is a really different kind of a question, and it's kind of a compounded question. So you're going to have to be pulling information from different places. And that is that as we learn more and more reactions, we are going to be able to start to have to devise how to synthesize a particular target molecule, beginning with whatever X, Y, or Z parameters that I give you. And this might not always be straightforward. Sometimes it might be straightforward, but sometimes it might be multiple steps that are needed. And in many cases, just like you would there's not necessarily one right answer in an essay question, there might be more than one right answer in a synthesis route type of a question. So these are just some things to kind of chew on as we go through chapter 6 and to keep in mind as we move on even forward from chapter 6. And the last comment that I want to bring up related to this pause and perspective is don't lose track. Don't forget to always go back to your fundamental concepts, the octet rule, the stereochemistry concepts that we learned in chapter 5. All of these things are still going to be important, and they will help you as you approach new reactions and have to think about new things. So before I get into chapter 6, I'm going to pause and make sure that nobody has any questions. This isn't really like information. It's more of a philosophical note, but just make sure that everybody is kind of coming with me on this shift in focus from general and fundamental features to specific reactions for specific functional groups. Okay, great. So moving on, this is what chapter 6 looks like. It is about the alkyl halides as a class, and we are going to talk a little bit about what those molecules look like as a class. We'll touch on the synthesis of alkyl halides, and we'll spend most of our time talking about the reactions of alkyl halides. So without further ado, this is what we're going to be doing today. Today, I'll give you a brief introduction to this class of molecules. I'm actually going to go a little bit out of order from your book, and I'm going to save the synthesis of alkyl halides for later in the week because I think it'll make more sense to go later in the week. And what I'm going to focus on instead of the synthesis for today is I'm going to focus on one variation of the reaction of alkyl halides after kind of giving you an overview of the types of reactions they can do. So without further ado, let's move on to introducing you guys to this class of compounds. Alkyl halides can really be broken down into 3 different structural categories, and then I'll break one of those categories down for you further. I'm going to show them to you all at once so you can see where we're headed. So alkyl halides is the name for the overall class. So every structure on this page is an alkyl halide, but we can break those down further into halogen atoms that are attached to sp3 hybridized carbons, which are also called alkyl halides. I know that seems weird, but this is kind of a subcategory of the bigger alkyl halide category. When that halogen is attached to a double bond directly, so directly attached to an alkene, then that's actually got a specialized name called a vinyl halide. And when that halogen is attached directly to an aromatic ring, like a benzene ring, that also has a special name called an aryl halide. These 2 types, the vinyl halides and the aryl halides, will not come into play very much during this chapter, but I wanted to introduce you to this terminology because you might see it every once in a while. Most of our focus is going to be on the halogens that are attached to an sp3 carbon. So this top group, I want to break down further for you guys into more specific subcategories. And these subcategories have to do with the substitution patterns on the carbon that the halogen is attached to. It's actually easiest if I start all the way over here to the right with the tertiary halides. If you look at the carbon that halogen is attached to, in the case of a tertiary halide, that carbon is a tertiary carbon because it's attached to 3 other things that are not hydrogen. So this terminology should feel really comfortable and familiar to everybody because we used a similar terminology for carbocations and a similar terminology for carbon radicals. So if the carbon where the halogen is attached has no other hydrogens attached directly to the carbon, that means it has 3 R groups attached, and that gives that carbon a tertiary carbon designation. And that means that if it has a halogen attached to that fourth position, it can be called a tertiary halide. Same thing with a secondary halide. That means that the carbon the halogen is attached to has two R groups, so two bonds to things that are not hydrogen, and then a hydrogen would fill that other vacancy. Primary halide, likewise, is when that carbon the halogen is attached to is only attached to one other R group. And the simplest case is when that halide is attached to a methyl group, so all of the other substitution features on that carbon are hydrogen atoms. So again, this should feel very comfortable and familiar to you based on the terminology you guys already know from carbocations and carbon radicals. In terms of nomenclature and IUPAC ruling, you guys also already know this, in fact. You apply the same exact rules that you do for alkanes to name alkyl halides. And just to point out, haloalkane is another way of saying alkyl halides. They're both consistent and they can be used interchangeably. But just like back in chapter 3, we need to find the longest carbon chain. Even if the halogen is not on that longest carbon chain, it does not matter. We still want to find the longest carbon chain. We also want to look for the lowest possible numbers for the position, meaning our substitution patterns should come closest to the start of their numbering chain. So here's one example here. We've got a 4-carbon chain here as our main chain. So of course that's a butane. And if we number this such that our substitution comes to the closest end, then we have a 2-chlorobutane. Again, butane for the 4-carbon unit and a chlorine in the 2 position. So we have a 2-chlorobutane. What about for this molecule here? Take a moment and count how many carbons and think about what the base name is for this molecule here. Take a moment, think on that for yourself. Okay, hopefully you came up with a base chain that is 7 carbons long. So what's the base name for a 7-carbon unit?
Heptane.
Great, it is a heptane. So we can number our heptane. In this case, it doesn't actually matter if we number left to right or right to left, because either way we number, we have a group coming off of the 4th carbon atom. And so then what do we do with that group coming off of the 4th carbon atom? Well, we need to figure that naming out. So if you guys recall, what we do is number that group coming off, where the number 1 is the carbon closest to the main chain. And once we do that, we can see that it's a 2-carbon unit, so it's an ethyl group, and it has a fluorine at the 2 position, so it's a 2-fluoroethyl group. And when we put that all together, we get the full IUPAC name for this molecule, which is a 4-2-fluoroethyl heptane. And again, 4 is the position where that substituent group is. 2-fluoroethyl is the name of the group because the fluoro is at the 2 position, and it's 2 carbons long, and that makes it an ethyl. Okay. Here's another example. I'm going to give you guys a minute to try this on your own, and then we'll talk through it together. This is not something you need to turn in. This is just for you guys to get a chance to give it a shot. Okay, so if you counted the longest carbon chain here, how many carbons in it, and what's the base name for that molecule? Okay, it is a nonane and there are 9 carbons, so that's great. Now that we know we've got a nonane base, we can give our numbering scheme and our substituent names. So hopefully everybody came to a place where they could name this compound as 6-bromo-2-methyl nonane using the numbering scheme up above. Why not number this molecule from right to left?
Because it has to be in alphabetical order.
Well, you just answered my second question here. So why not 2-methyl-6-bromo nonane is alphabetical order? Bromo has to come before methyl in the name. But why not number it right to left so that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's right. So the substituents have to be as low in numbers as possible, meaning the first time you get to a substituent has to be closest to the end that is where you start your numbering, closest to the end carrying carbon 1. So our methyl group is at the 2 position, but of course it has to go second in the name because it comes after bromo, which is at the 6th position. Okay, here's another example for you guys to give a try. Take a moment and give it a shot on your own. Okay, what's the base carbon structure here? What's the scaffold name, the main chain or scaffold name for this molecule?
Cyclohexane?
Good, cyclohexane. So then when we number our cyclohexane, we just pick one of our substituents and make it number 1. And then we number around the lowest, so we get the lowest numbers. So in this case, I picked the bromo to be number 1, and I numbered around the circle in a clockwise fashion, as it's drawn here, to get cis 1-bromo 3-fluorocyclohexane. And so I've given it a cis designation because our two hydrogen atoms are on the same side of the ring. This is a cis 1-bromo 3-fluorocyclohexane. And this is not actually the full IUPAC name of this molecule. So I do want you guys to challenge yourself, and offline after class, I want you to take the time to assign R or S stereochemistry to these centers and recognize that the actual IUPAC name would give an R and S designation to the 1 position and to the 3 position that would appear out front here instead of cis, or in addition to cis. Okay, so we've talked about what alkyl halides are and how to name them. Now I want to get into a little bit more of the chemistry of alkyl halides, the structural features of alkyl halides. So this slide is really going to represent the structural feature of alkyl halides that really underscores and underlays their reactivity. So in every alkyl halide, there's going to be a carbon-halogen bond. And what we already know from chapter 2 about those carbon-halogen bonds is that they are highly polarized, right? We know all of the halogens have a high electronegativity constant. They are all much more electronegative than carbon. And so every single alkyl halide will have a strongly polarized carbon-halogen bond. That means that the carbon associated with that carbon-halogen bond is going to be delta positive. It's going to have a partial positive charge. Another way to think about that is that it has a lack of electron density. Well, what does it make it? What does that make that carbon? It makes that carbon an electrophile, right? If that carbon is lacking electron density, then that carbon is going to be an electrophile. It's going to want to bring electrons toward it. That means that that carbon can be attacked by a nucleophile. When that happens, if we look closely at this alkyl halide, what happens when a nucleophile comes in and tries to make a new bond with that central carbon? Well, you would have 10 electrons and you'd break the octet rule. So we know that that cannot happen because we are not allowed ever to break the octet rule for carbon. And so in order for our nucleophile to come in to this electrophilic carbon and make a new bond, we have to break another bond. And the bond that makes the most sense to break is the one with the halogen, because that halogen can leave with the electrons that are in that bond and leave as a Cl minus, a chlorine minus, and be pretty well stabilized because of its strong electronegativity. And that's indeed what happens. So this is just another example where the things that we've already learned about fundamental properties and structure can tell us something about how a molecule is going to react. So I want to put this slide up. This is a similar slide, something I showed you guys back in a previous chapter, that dipole moments of bonds have to do both with the electronegativity difference of the two atoms participating in the bond and the bond lengths. And it turns out that for alkyl halides, those two trends are competing, right? The electronegativities of the halides are most and highest at the top of the periodic table, but the bond lengths with carbon and halogen bonds increase as the size increases, so as you go down the periodic table. And so these two trends, both of which contribute to the dipole moment, they're competing. And so it just makes the dipole moment trends for carbon halogen bonds a little bit less obvious. So I've listed out what they are here based on the actual bond dipoles. I do not want you guys to memorize this. I am not asking you to memorize either these values or this order. The only point of this slide is to make sure that everybody understands that those dipole moments connect both with electronegativity and with bond length, and that those two different trends are competing with each other and making the trend of actual bond dipoles a little bit more challenging to predict. The other point of this slide is to remind everybody that the bond dipole does not have to be the same as the molecular dipole, and in fact, often is not the same. The molecular dipole, the overall molecular dipole, depends on the geometry of the molecule and on the addition, the kind of conglomeration of all of the dipoles of every single bond in the molecule. So you can see in this example, carbon tetrachloride, you have 4 highly polarized bonds, right? But they all are oriented in a geometry such that they cancel each other out, and carbon tetrachloride is overall non-polar. All right, so the last feature or property that I want to mention about halogens or alkyl halides is that if you pop a bunch of halogen atoms onto a scaffold, you can actually get some really neat properties with respect to the density. So if you have compounds that have just one halogen atom, then those are normal organic compounds that have a lower density than water. But as soon as you put on 2 or more chlorine atoms, or if you put on a bromide or an iodide, these halogens impart a higher density on the organic solvent. And so a lot of times these halogenated solvents can be put into use in organic chemistry. So if we have, for example, if we put 2 chlorines onto a single carbon, then that gives us dichloromethane. If we put 3 chlorines on, that could be called trichloromethane, but the more common name is chloroform. And if we put 4 carbons on, that would be carbon tetrachloride. All of these chlorinated solvents, and also every alkyl bromide and alkyl iodide, are heavier than water. And what that means is that if you're in the lab, you can actually separate out water from organic solvents. And hopefully you guys have had this experience either in real life lab courses or in online virtual lab courses, where you can separate out and extract your organic products into an organic solvent and wash away whatever aqueous soluble byproducts or reagents that you have. So almost all organic solvents are lighter than water and will separate out as kind of a biphasic solution on top of the water layer, just like oil and water would. But these halogenated solvents are heavier than water, and so they'll actually separate out in a biphasic system at the bottom. And so there are 2 consequences of this. One is that we need to make sure as organic chemists, we know which kind of a solvent we're using, so we know where to look for our organic molecules to be dissolved. And 2 is that we might be able to choose a more appropriate solvent depending on what we want to do. So if what we want to do is do a lot of aqueous washes to get out a lot of aqueous soluble reagent leftovers, we might be better off with a lighter solvent, because we can continue to add aqueous, shake, and then remove the bottom, add aqueous, shake, and then remove the bottom. Whereas if we want to use an organic solvent to extract as much as we can of our organic material out of an aqueous phase, we might be better off with a heavier solvent, so we can add organic solvent, shake and pull our organic extracts and do that repeatedly. So we can make a choice based on what we already know about the features and properties of these alkyl halides. I'm not going to test you on this slide here, but I did want to put up a slide showing the use of alkyl halides, just kind of as a real life interest, connecting our organic chemistry with real life applications, because alkyl halides are in use in a lot of different places, such as anesthetics. Chloroform was historically used as a medicinal anesthetic. Now it shows up on crime shows all the time to knock people out. Freons are used as refrigerants or foaming agents. So in your AC unit, older AC units used to have fluorinated alkanes as the refrigerant. Those are now being replaced by a lot of more environmentally friendly things, but they were still in use for a long time. And then finally, pesticides are a common place where you'll see alkyl halides because they can get incorporated by bacteria, but not processed. And so they can be toxic to bacteria. And it turns out really with all three of these categories, the human effects of alkyl halides have been recognized more and more lately. And in all three of these categories, newer and better methods are being developed to improve human health and avoid human exposure to alkyl halides. Okay, so that covers our first part of today, where we were learning and kind of meeting alkyl halides for the first time in an in-depth way. I'm gonna, like I said earlier, I'm gonna jump over synthesis. We're gonna save that for later in the week. It's gonna make more sense to do later on. What I wanna do now is give you an overview of the types of reactions that alkyl halides can do, and then we're gonna hone in on just one type of one of these reactions. And we'll look at it pretty much in depth for the rest of the class today and a little bit on Wednesday. So in terms of thinking about what alkyl halides can do, the reactions of alkyl halides fall into two broad categories. The first, which is the focus of this chapter, is called nucleophilic substitution. And the overall reaction looks like this, where we have an alkyl halide and that carbon-halogen bond ends up being replaced by a carbon nucleophile bond, and the halogen is released with the electrons that were in that bond. The other type is called elimination, and it's not even part of this chapter. So you don't have to worry about it right now. It's not going to be on exam 2. It's going to be the focus of chapter 7. But just for kind of completeness sake, I will show you guys that we're starting with the same alkyl halide. And the end result is that we're, instead of replacing that halogen, we're going to remove a proton from a neighboring carbon and the halogen. So we're going to make a new double bond with 2 of those electrons, and the other 2 electrons will go with the halogen to give a leaving group. So again, you don't have to worry about this bottom half right now because that's chapter 7 and it's not even part of exam 2. But this top part is where our focus is going to be for most of chapter 6 on nucleophilic substitution reactions. And there are in fact 2, well, there's actually more than 2, but for this chapter, we're going to focus on just 2 different mechanistic pathways for this type of overall reaction. And I'll call them different reactions, but the overall reaction category of nucleophilic substitution is the same for both of them. So here's the 2 reactions that we're going to learn in this chapter. The first one is called SN2, and this is a particular mechanistic variation on a nucleophilic substitution. It's called SN2 because it's a bimolecular nucleophilic substitution. That's actually, the S is for substitution, the N is for nucleophilic, and the 2 is for bimolecular. And the reason it's called a bimolecular is in the rate limiting step, or the first, in this case, the first step of the reaction, 2 different molecules have to come together to get this reaction to go. You have a nucleophile and an electrophile coming together to undergo this reaction where, again, we're creating a new carbon nucleophile bond and our halogen is leaving with the 2 electrons that used to hold it attached to the carbon. So we'll focus in on this one for most of the rest of the time today, but I just want to contrast it with the SN1 mechanism so you kind of see where we're headed. Again, this SN2 is bimolecular because both the nucleophile and the electrophile are involved in the rate determining step. In contrast, in an SN1 mechanism, the rate determining step is unimolecular. So it doesn't involve two molecules, it just involves one molecule. And the way that works is that our alkyl halide literally just breaks its carbon halogen bond in the rate limiting step. So in the rate limiting step for this SN1 reaction, the nucleophile is not involved at all. It only involves just one molecule of the alkyl halide decomposing, and then you're creating a carbocation that the nucleophile can then attack. Don't worry about this right now. We're going to talk more about the SN1 on Wednesday. For today, we're going to focus all of our attention on the SN2 mechanism, this bimolecular version of nucleophilic substitution. So with that, I'm going to get into this very, very specifically for SN2. Again, here's the overall generalized nucleophilic substitution reaction, where we have a nucleophile, such as hydroxide, interacting with an alkyl halide, which is, again, electrophilic at the carbon center. We're going to form a new bond between our nucleophile and our electrophilic carbon. You can see that new bond right here. And we're going to release an halogen, a halide actually, with the two electrons that were part of the bond holding it on to the carbon atom. So that's the overall reaction. Again, it's called nucleophilic substitution because the halogen is replaced by or substituted by the nucleophile. The halogen is obviously more electronegative than the carbon. So this highly polarized bond, when it breaks, is going to break so that those two electrons go with the halogen. I've already mentioned this, but I want to be clear and explicit about it. It's called an SN2 because it stands for substitution, that is the nucleophilic type, and bimolecular, that 2 refers to it being bimolecular. And the reason it's called bimolecular is that 2 molecules are involved in the rate determining step. So someone's asked in the chat box, would it matter if you placed the OH minus on the right or the left to get the methanol product? That's a great question. In the SN2 reaction, there are stereochemical consequences because of the mechanism, and we'll see that over the next couple of slides. So stay tuned. Okay. The mechanism for SN2, as I've already talked about, involves both a nucleophile and an electrophile coming together in the rate determining step. So it involves both molecules. What we have is, therefore, the bond between our nucleophile and our electrophilic carbon forming at the same time and at the same moment that the bond between the carbon and the halogen is breaking. This has a term, it's called a concerted reaction. And if you think about it as the bonds being formed and the bonds being broken are happening in concert with each other, then it might help you remember the term concerted reaction. All right, the reaction, as I said, it's bimolecular, so it's second order overall with a rate that is dependent on the alkyl halide and the nucleophile, right? So it is second order, first order in alkyl halide, first order in the nucleophile, and bimolecular or second order overall. Now, because we are forming this bond and breaking this bond at the same time, there are stereochemical consequences to that, and that's going to be a key feature of an SN2 type reaction. So you can see I've drawn out the transition state here, where we have our nucleophile and electrophilic carbon bond partially formed, and our carbon and halogen bond partially broken. And if you think about the geometry required for a tetrahedral center, where if we have our carbon halogen bond oriented directly off to the right, our remaining 3 substituents would all 3 be kind of pointed to the left, right? But if we go through a transition state where our nucleophile is coming in from the left-hand side, forcing all 3 of these substituents into a kind of a planar configuration, Then when that leaving group leaves and our new bond has come in from the left, and so our new bond is facing the left, our three remaining substituents kind of have to flip around to the other side to maintain that tetrahedral geometry that's needed at the end point. So that might have seemed confusing the way I was saying it, but I'm going to show you pictures on the next couple of slides that'll helpfully clarify. Before I get there, I just want to remind everybody about the energy diagram for this reaction, that because it is concerted, there's only one step in the overall reaction. We start out with our reagents or our reactants, our nucleophile and our electrophile, or our nucleophile and our alkyl halide. We go through a single mountain transition state and come out to our products on the end. So there's only one hump in this reaction because it is a one-step reaction. And again, that transition state where we have partially formed and partially broken bonds is going to be the moment where we're at the highest energy or the peak of that mountain. Okay, in terms of these mechanistic considerations or the stereochemical consequences, I want to show you guys a couple different ways to look at that and think about that. For SN2 reactions, these reactions will always, and I mean always, and I don't get to say that very often in organic chemistry, SN2 reactions will always result in inversion of the configuration at a stereochemical center. So if you have a chiral center as your alkyl halide carbon, then when your nucleophile comes in and these substituents go through this kind of forced planarity in the intermediate, and then flip, sorry, this is not an intermediate, that was my mistake. This is a transition state. They go through this forced planar transition state with these three substituents all in the plane perpendicular to the page. And then in the product, they flip over in order to accommodate our new carbon nucleophile bond and maintain a tetrahedral center. So if you notice, the ethyl group, which was coming towards you in the starting point molecule and off to the left, it's stayed coming towards you the whole time, but it's now shifted from the left-hand side through the middle and off to the right. Same thing with the methyl group. It was going back and to the left, and it shifted through the middle, and now it's back and to the right. So overall, we've inverted the stereochemistry of this center. This inversion always occurs, whether or not this carbon is chiral. But if the carbon is chiral, then the mechanism of an SN2 reaction means that the stereochemistry of your product will have an inverted center at that chiral carbon, which means that you might actually change the RRS designation of your material. And you will always, and certainly always, flip the stereochemical configuration. So what do I mean by what I just said? In this example that we have here, when we do our inversion because of the SN2 reaction, we do indeed have a situation where our S stereocenter becomes an R stereocenter. But I just want to take a moment and be explicit about this and remind everyone that the S and R designation are dependent on the priority groups, the four different prioritization of the four different groups surrounding that chiral carbon, right? And so in the example that's shown here, and in many examples that you will see, the priorities didn't actually change because over here in our starting material, bromine is the top priority, the number one priority. And in our product, our nucleophile has our number one priority designation. Because those priority numbers did not change and the 2, 3, 4 did not change, that means that we went from an S configuration to an R configuration. If the priority numbering changed when we introduced a nucleophile as opposed to a leaving group, it's possible that your R doesn't become S, that it stays as R or it stays as S. It's possible that you can get this inversion without changing the RS designation if the priority groups change. I know that possibly was confusing. So I'm going to pause and let you guys ask a question if you need to.
My question is, so regardless, I know it's gonna change like which side it's on, right?
Yeah, the stereo center here will be inverted. That carbon center will be inverted.
Okay, so but if it's chiral, it may not just change sides, it'll also change if it's RNS, RS.
It's possible, and usually it will change RRS, but remember that R or S designation has to do with the priority. So what I'm trying to say here is that in this example, both the leaving group and the new bond that you're forming are number one priority of the 4. And so it won't actually change the prioritization scheme. So you'll see that inversion reflected in S going to R. But if, for example, we used a nucleophile that had a number 2 designation, then we would have to renumber everything and figure out S and R independently. Does that make sense?
Yes, so it's possible to change, but it still has the same rules applied to it.
Exactly. Yeah, you always have to apply the prioritization scheme for Con-Angle Prelog to get S and R designation, right? So what will always happen is that you will always, in an SN2 reaction, go through this planar intermediate and flip your 3 remaining substituents around to the other side. And I'll show you an example of that, I think, on the next slide, which might help. So let me show you that. Yeah. Okay, so focus your attention down here on the bottom of this slide. This is what I call an umbrella flip. So you can kind of see here how the 3 remaining substituents that are not your alkyl halide, not your carbon halogen bond, the other 3 are oriented kind of in an umbrella where they're all pointed to the left if your carbon halogen bond is pointed to the right. When your nucleophile comes in, it's going to come in opposite side from the carbon halogen bond. And so when it does that, it forces those 3 substituents to flip over the same way an umbrella would flip over when it's really windy outside and turn to the opposite direction. Does that make sense? So you can see it also here in a more orbital type version where you have your nucleophile here. That nucleophile has to come in opposite from your carbon halogen bond. It's actually going to be aiming for this back lobe of the hybridized orbital. We don't always draw that back lobe, but in this case, we have it drawn here so you can see where this is going. And when those electrons from your nucleophile come in to fill that back lobe of this electrophilic carbon bond, you'll go through this transition state. The halide will be released with the 2 electrons that were in the carbon-bromine bond, and the 2 electrons from the lone pair of the nucleophile will create the new bond between carbon and oxygen. And so you can see here all of the orbitals involved, and you can also see how we're going through a flip of the stereochemical center here. So I didn't realize I'm a couple minutes over. I'm sorry about that. This is where we're going to stop here for today, and we'll pick up here with other features of the SN2 reaction on Wednesday, and we'll also start in on SN1.
Thank you. Have a good day.
Thank you, guys. You too.